This video is an introduction into stereochemistry. We will look into isomerism, chirality, and nomenclature of chiral compounds. First, when we consider isomerism, we should briefly review types of isomers, which you should be also already familiar with from a general chemistry course. So, constitutional isomers are isomers that have same molecular formula, but the connections among their atoms are different. Old name for constitutional isomers is structural isomers. So, in simplest terms, constitutional isomers have same molecular formula but different structural formulas. That's why they used to be called structural isomers. There are three types of constitutional isomers. Skeletal isomers have carbon skeletons that are different. Positional isomers have identical carbon skeletons, but positions of functional groups are different. And finally, functional isomers have same molecular formula but different functional groups. So here you have those three examples shown as condensed formulas. Now the same examples are shown as line formulas. And you can see how much easier it is to identify each type of isomers from the corresponding line formula. So skeletal isomers, clearly from line formula, you can see two skeleta are different. Positional isomers, clearly you can see that we have straight chain of 5 carbon atoms in each compound, so identical carbon skeletons, but OH group is in different position. And finally, functional isomers, that's easy to see that these two compounds have different functional groups. Another class of isomers are stereoisomers. Stereoisomers have identical molecular formula, but different arrangement of atoms in space. There are two types of stereoisomers: conformational isomers and configurational isomers. Configurational isomers, in turn, are divided into two classes: into cis-trans isomers, old name is geometric isomers, and optical isomers. Now, when it comes to stereoisomers, conformational isomers, or just conformers, can be interconverted into each other by bond rotation. And since they are readily interconverted into one another at room temperature, they cannot be separated and isolated. So if we have one conformer, it will very quickly convert into the other and will have equilibrium mixture of individual conformations. So for that reason, usually conformers are not considered to be true isomers. We studied conformers in chapter 4 when we did conformational analysis. And here is an example of two conformers of propane. So here you can see eclipsed and staggered conformations of propane. We will not be looking at conformational isomers anymore. We have already done that. And here is a summary of isomerism. So isomers can be classified as constitutional and stereoisomers. Constitutional are further subdivided into skeletal, positional, and functional isomers, while stereoisomers could be configurational or conformational. Configurational are subdivided into cis-trans and optical isomers. If you wish to study this table and this division in more detail, you can pause the video here and look at it in bit more detail. I'm going to now move on to optical isomers. In this chapter, we are going to look at optical isomers. And optical isomers are consequence of chirality of molecules. So we need to examine what is chirality and how to identify chiral molecules. So first, let's look at property of superimposability and how it is related to chirality. Superimposability simply means overlapping. Can we get two molecules to superimpose on each other, to overlap on each other so there is perfect match, that each atom matches same atom in another molecule? So it's obvious that isomers are non-superimposable. Obviously, if they were superimposable, they will be identical. Superimposability also means identity. So if two molecules are superimposable on each other, it means they are identical because they are perfectly overlapping. So obviously, isomers cannot be superimposable. So in this case, we have cis-trans pair of isomers, and clearly they are not superimposable. when we try to place one over the other, we can see that there is mismatch, in this case on the right, between bromine and hydrogen atoms. Identical molecules are superimposable, so when we place one over the other, there is perfect match. And then when we have two mirror images, so you see two structures on the left, they are actually mirror images of each other. The way they are represented, it may not be obvious they are mirror images, but if you make models, you will see that two of them are mirror images of each other. And they are non-superimposable. Sometimes mirror images are superimposable on each other, sometimes they are not. If two mirror images are non-superimposable on each other, then they are enantiomers, or optical isomers. So that's the definition of optical isomers, mirror images that are not superimposable. Whether two molecules are chiral or not, so whether they are superimposable mirror images or not, we can determine by looking at symmetry of the molecule. Molecules that are asymmetric, that have no symmetry elements, will be chiral, will be non-superimposable to their mirror images. And we look at specific symmetry elements. So the most importantly, we look at presence of plane of symmetry. That's the plane that bisects molecule into two equal halves and reflects one half into the other. So if molecule has plane of symmetry, it is not chiral. Here we have molecule of ethanol, and you can see a plane that goes through OH group, carbon atom, and CH3 methyl group. So that plane bisects the molecule in half and reflects in CH2 group one hydrogen into the other. So that's the plane of symmetry. Since ethanol has plane of symmetry, it is not a chiral molecule. Other elements of symmetry that will render molecule non-chiral are center of symmetry. So center is point at the center of the molecule that reflects each atom or each point, each structural element of a molecule into corresponding element at the same distance from the center at the other end of the molecule. It's shown here in light blue. So this cyclic molecule has a center of symmetry. For that reason, it is not chiral. And finally, maybe the most complex symmetry element is alternate axis of symmetry. Alternate axis of symmetry is axis that goes through the center of the molecule, and when we rotate one half of the molecule, in this case let's say right half, right 5-membered ring, by certain number of degrees, in this case let's say 90 degrees, and then reflect that half through a plane of symmetry that is at 90 degrees to axis of symmetry, then it will perfectly reflect to the other half of the molecule. That's alternate axis of symmetry. It's a little bit complex and a little bit difficult to identify. If molecule has an alternate axis of symmetry, it is not chiral. So those are three elements of symmetry that molecule must not have to be chiral. So if it does not have any of these three elements, then it's not superimposable to its mirror image. For larger molecules, this is actually what we look at. We look at these symmetry elements, and if they are not present, molecule is chiral. If they are present, molecule is not chiral. For you, in this course, actually you should be looking only at plane of symmetry. Center of symmetry and alternate axis of symmetry are more advanced concepts, and you won't need them. So to answer questions in this course, in introductory organic chemistry course, only look for plane of symmetry. Now keep in mind that chirality means non-superimposable mirror images. So real test is making two models or looking at two molecules and see whether two mirror images, so making two mirror images and seeing whether two mirror images can be superimposed. If they cannot, molecule is chiral. If they can, it is not chiral. Symmetry is only consequence of it, and we are looking at symmetry elements because that's easier than making, let's say, large models or other complex models. In a chiral molecule, we can identify center of chirality. That's a point in space that is responsible for asymmetry of the molecule. And typically, that center of chirality overlaps with carbon atom. An example of molecule with one center of chirality would be 1-chloroethanol. So it has a center of chirality that overlaps to carbon atom with carbon atom 1, that's carbon attached to OH group. And you can see two non-superimposable mirror images in this yellow box. So a dotted line represents a mirror, and you can see clearly two mirror images, and they are non-superimposable mirror images. So this molecule exists in form of two optical isomers or two enantiomers. Enantiomer is a name for optical isomers. Note that two isomers, two mirror images have to be represented properly to show that they are two different isomers. Here, in this blue box, we have representation of the same enantiomer. So those are two representations of the same molecule. Clearly, you can see that they can be superimposed on each other. So that's representation of the same isomer. So even though this is chiral compound, these two formulas represent the same enantiomer. Distinguish that from non-chiral molecule, like ethanol, where any representation of ethanol will represent the same molecule. So regardless of whether we represent ethanol as two mirror images or as on the right, it's the same molecule, since this molecule does not exhibit chirality, does not exhibit optical isomerism. Typically, chirality center is indicated by an asterisk, and as I said, it usually overlaps with the carbon atom. For that reason, we often talk about chiral carbon atom or asymmetric carbon atom or something, use terms like that. Keep in mind that atom itself is perfectly spherical and cannot be chiral or asymmetric, but those are convenient terms that we usually use, and we all know what they mean. From this discussion so far, you may have already drawn a conclusion that chirality center, asymmetric center, chiral carbon atom is carbon atom that has four different substituents. So for that reason, carbon atom must be sp3 hybridized. That's one that has four different substituents. And here are some examples. So when you look at the line formula, for example, that's what you'll be looking for when looking at chirality centers. Whether there are four different substituents on the carbon, and of course keep in mind that we don't represent hydrogen. So here are several examples. You can pause the video here if you want to examine them more and maybe redraw these formulas as, let's say, condensed structural formulas or in some other form to show all the substituents. And note that the last example, 5-amino-2-heptanol, has two chirality centers. Now, while chirality center usually overlaps with carbon atom, chiral carbon atom, or overlap of chirality center with carbon atom is not necessary for molecule to be chiral. And there are several examples where chiral carbon atom is absent. So allenes are chiral. They exist if they have different substituents on each carbon atom of an allene molecule. Allenes are cumulative dienes, where carbon atom is common to two double bonds. In this case, we actually can say that middle carbon is actually chirality center, but it doesn't have four different substituents. So in this case, you can make models and convince yourself that these molecules, these two isomers, are indeed two enantiomers. Then another example is biphenyl, where each benzene ring has two different substituents. In this case, chirality center is at the middle of the bond that connects two benzene rings. And finally, helicene molecules are an example of molecule where chirality center is point in space, somewhere in the middle between these fused six-membered rings. Cyclic compounds could also have chirality centers and be chiral. And chirality center may be part of the ring. So you should be able to identify such atom. So what you do is you look at atoms in the ring, carbon atoms of the ring, or possibly other atoms that have four different substituents of the ring that you suspect are chirality centers. Those would be atoms that have two different substituents, and then remaining two are, of course, form part of the ring. So you have identified two substituents, and those are substituents that are outside the ring. And then, starting with carbon atom in question, you draw a line to divide ring into two halves, two equal halves. So simply bisect ring into two equal halves. That means equal number of ring atoms, even if atoms are different. So in this case, six-membered ring is divided into two halves. Each half has two atoms of its own. remaining two atoms are common to both halves. They are bisected by the line that divides ring into two halves. And now we look at those two halves. Are they identical or different? We don't count atoms that are common to both halves. Look only to atoms that are unique to each half of the ring. We can see that one half, top half, contains oxygen atom, bottom does not. That means two halves are different, and as a consequence, carbon atom we were examining is chirality center because it has four different substituents. So we label that as chirality center and note what it would look like in a line formula. So this compound has one chirality center. Here are some examples of cyclic compounds, quite a few of them, and chirality centers. Again, last example has more than one chirality center. You may want to pause video here and look at each of those examples in detail and do determination of chirality centers of each compound on your own by dividing each ring into halves and comparing the two halves and seeing how they are different. Sometimes the difference between the two halves of the ring is rather subtle. Nonetheless, you should be able to recognize that two halves are different. So for example here, when you look at two halves of the ring, they have two substituents. When we divide five-membered ring, as you'll see in a minute, into two halves starting at atom here that has already been labeled as chirality center, you will see that two substituents have different configurations. So you see there are two substituents outside the ring that are clearly different, methyl group and hydrogen. But then when we divide ring into two equal halves, in this case, line that divides ring into two equal halves would go to the middle of the bond between carbons 3 and 4. So you can see that one substituent, one on the left is trans, and one on the right is cis. That makes them different. So two halves are different, and therefore this molecule is chiral, and atom that we are examining is indeed a chirality center. In another, even more complex example, rather similar, two substituents that we have are also different because they have different configurations. Each substituent itself is actually a chirality center. This molecule has three chirality centers, and molecule in the middle, molecule of the ring, atom of the ring, atom in the middle, atom of the ring is also a chirality center, and that's because two substituents are two chirality centers and they are different. They are non-superimposable chirality centers. That being the case, then the ring atom that we are examining is also a chirality center. Finally, in this example, there are two chirality centers, and actually starting at each atom that is a chirality center, when we divide ring into half, it's clear the two halves are different. I included here because for some reason students have tendency to make mistake here and not realize that there are two chirality centers here. So each of the labeled atoms is a chirality center. So again, you may want to pause video here and analyze this molecule a little bit more to convince yourself that there are indeed two chirality centers. As already mentioned, stereoisomers that are related to each other as two non-superimposable mirror images are called enantiomers. It means that the term enantiomer means the same as mirror images. Enantiomers can be converted into each other only by breaking of covalent bonds. And here is example of representation of two enantiomers using perspective formulas. So to represent enantiomers in two dimensions, for example, we can use perspective formulas, and here are several examples, several ways where we can represent enantiomers. In this case, we have two enantiomers of two pentanol. Top row shows one enantiomer and bottom row the other enantiomer, and shows how we represent two enantiomers. So all of these are perspective formulas. On the left we have condensed drawing, and in the middle and on the right there are line drawings. In the middle we have line drawing that shows hydrogen at the chirality center. That hydrogen does not need to be shown. Sometimes we show it as a courtesy to a viewer to emphasize that there are four different substituents. More commonly, we represent 2-pentanol with formula on the right. And so you are supposed to be able to recognize 2-pentanol as chiral compound and that top and bottom formulas on the right represent two enantiomers. Another common way to represent chiral molecules is by Fischer projections. Fischer projections are formulas where chirality center is in the plane of the drawing. So in this case, plane of the paper or plane of the screen. And then we draw four substituents simply as a cross, as vertical and horizontal lines, as two vertical and two horizontal bonds. They are drawn as or represented as solid bonds, but they have meaning, three-dimensional meaning, perspective meaning. And so corresponding perspective formula is shown on the left and Fischer projection on the right. So horizontal bonds project towards the viewer, which means that using perspective formula, they would be represented as wedge bonds. And vertical bonds project away from the viewer. So using perspective drawing, they would be dashed bonds. So only chirality center is in the plane of the drawing, and the vertical and horizontal bonds either project vertical away from the viewer, horizontal towards the viewer. So you have two examples, top and middle, with single chirality center. If there are two chirality centers, two neighboring, two contiguous chirality centers, and that's contiguous, not contagious. Contiguous means neighboring next to each other. Then, of course, since each chirality center is in the plane of the drawing, then bond that connects them must also be in the plane of the drawing. Horizontal bonds are still projecting towards the viewer, so those would be wedge bonds in perspective drawing, of course just solid line in Fischer projections, and then terminal vertical bonds, those at the end are projecting away from the viewer. In perspective formula they would be dashed. So note that in Fischer projection, that's obvious from perspective formula, molecule is in less stable eclipsed conformation, and actually for stereochemical analysis that's beneficial, while conformationally that's not very stable conformation. This is actually really good for stereochemistry, for stereochemical analysis, as you will see later. Now, to memorize which bond is vertical, which is horizontal, which projects towards the viewer, which away from the viewer, we use bow tie convention. So if you imagine a bow tie is obviously horizontal, so in this case we have Emil Fischer's bow tie. So two horizontal bonds with two wedges look like a bow tie. And so you can memorize a bow tie convention. The two horizontal bonds look like a bow tie and project towards the viewer. And of course that leaves vertical bonds projecting away from the viewer. So what happens if we have a couple of contiguous chirality centers? How can we memorize that? Well, we can easily memorize that by using a small animal convention. So in this case, you have Fischer projection on the right. So question is which bonds project towards you, which away from you. And so to the left, you have perspective drawing, which shows which bonds project towards you, which away from you. But to know that, you would have to know, to draw that, you already have to know which project towards you, which away from you. And you will know that by remembering a small animal convention. And that is, if you imagine somebody's throwing a small animal at you, its legs will be projecting towards you, while its head and tail away from you. And so that's a very easy way to memorize which bonds project towards you, which away from you. This completes introduction into stereochemistry, and next we will be looking at configuration and nomenclature of enantiomers.